Let me start with something simple. Have you ever noticed how you get a tiny shock when you touch a metal object after walking on a carpet? That little jolt, that's electrostatics in action. Now imagine you're trying to move a tiny positive charge closer to another charge that's already sitting somewhere in space. If the charge you're approaching is also positive, you have to push against the repulsive force, and that means doing work. This is where the idea of electrostatic potential comes in. In physics, we define it as the work done by an external force in bringing a unit positive charge from a place infinitely far away to a point near a source charge without changing its speed. We denote this by the formula V equals W divided by Q naught, where V is the potential, W is the work done, and Q naught is the test charge. Now why from infinity? Because at infinity, the effect of the electric field is practically zero, so it gives us a clean starting point. And here's something neat, electrostatic potential is a scalar. It doesn't care about direction, just about the amount of work. It can also be positive or negative, depending on whether you're dealing with repulsion or attraction. Alright, now let's zoom in on a very specific situation, just one single point charge. What would be the electric potential around it? The formula is V equals 1 by 4 pi epsilon naught multiplied by Q over R, where Q is the point charge and R is how far you are from it. This means the closer you get to the charge, the higher the potential. And as you move farther away, toward infinity, the potential drops down to zero. Now, if the source charge Q is positive, the potential around it is positive. If the source is negative, the potential becomes negative, indicating an attractive interaction for our test charge. You can picture this as concentric spheres around the charge, each one representing a level of potential, like contour lines on a topographic map. Okay, that was just one charge. But in real life, and in most physics problems, we often deal with more than one charge. So how do we find the total potential at a point due to multiple charges? The good news is potential is a scalar. So we don't need to worry about directions or components. We just add up all the individual potentials algebraically. This is known as the superposition principle, and the formula is V equals 1 by 4 pi epsilon naught multiplied by the sum of Qi over Ri, where Qi is each charge and Ri is its distance from the point we are interested in. Let's say you have two charges, one positive, one negative, placed around point P. Each creates its own potential at P, and you simply add or subtract based on their signs. Simple, elegant, and extremely powerful.
Now comes one of the most interesting and elegant charge systems in electrostatics, the electric dipole. Imagine placing a positive and a negative charge, equal in magnitude, but separated by a small distance, say 2a. That's a dipole. Now we ask, what's the potential at some point in space around this dipole? Here's the key equation. V equals 1 by 4 pi epsilon naught multiplied by p cos theta over r squared, where p is the dipole moment, given by q times 2a, r is the distance from the center of the dipole, and theta is the angle from its axis. So unlike a single point charge, the potential here depends on both distance and direction. A very cool thing happens on the equatorial line, the line perpendicular to the axis of the dipole. Here, the contributions from the positive and negative charges cancel out, giving zero potential. You can visualize this with field lines. The dipole's field is not radial, but curved and symmetric.
Let's shift to a visual concept now, something called equipotential surfaces. These are surfaces where the potential is the same at every point. That means if you move a charge along such a surface, you don't do any work, because there's no change in potential. Here's an important property. Equipotential surfaces are always perpendicular to electric field lines. Why? because electric fields only do work along their direction, not across it. Some classic examples: around a point charge, equipotentials look like concentric spheres. In a uniform electric field, like between capacitor plates, they're parallel planes. And if these surfaces are packed closely together, it means the electric field is strong in that region. This gives us a really nice visual understanding of field intensity. Time to apply what we've learned. Here's a challenging question. You have a square of side 2 meters with charges placed at each corner. Two opposite corners have plus 2 microcoulomb and the other two have minus 2 microcoulomb. What's the potential at the center of the square? Let's solve it step by step. In step 1, from the center to any corner, the distance is √2 meters. In step 2, use the formula V equals 1 by 4 pi epsilon naught times sum of Q over R. Since two charges are positive and two are negative, and each is at the same distance, their potentials cancel each other out. So the total potential is 0 volts. That's the beauty of symmetry. Even when charges are present, the net potential at certain points can be 0. Alright, let's wrap it all up. We began by understanding that electrostatic potential is all about the work done in moving a unit positive charge without acceleration. For a single point charge, the potential is inversely proportional to distance, V equals 1 by 4 pi epsilon naught times Q over R. Then we explored how to handle multiple charges using the superposition principle, followed by the fascinating case of the electric dipole, where direction also plays a role. Equipotential surfaces gave us a visual map of how electric fields behave, and finally, we solved a numerical that showed how symmetry can lead to a zero potential even when charges are present. This concept is foundational. It sets the stage for capacitors, potential energy, and electrostatic shielding, all of which are just around the corner. So stay curious, keep questioning, and I'll see you in the next session where we'll dive even deeper into the electric world of physics.